This inverter gate which takes only one input signal and always gives only one output signal. There are two types of logic gates. One is basic gates, second one is derived gates. In the truth table, we are writing the possible input combination of a variable along with its result or output. Dear students, welcome to Computer Science Revision classes. I am Ravi Kumar KR, lecturer in Computer Science, Vidhyaashram PU College, Temple of Excellence, Mysuru. Students, in this revision class, today we will talk about the chapter Logic Gates, chapter number 3. Now, the weightage of the chapter is 9 marks. You have one MCQ or one question, MCQ question or 1 mark question, and 3 marks question, and here this is 1 5 marks question. So here total weightage of this question is 9 marks. This is the weightage of the chapter. Now let us start with the definition of logic gates. Now in this chapter we are going to talk about logic gates. Logic gates are nothing but electronic circuits, and this is what we have seen inside our microprocessor or integral ICs, IC chips. So inside an IC chip, it is made up of number of electronic circuits. All these are made up of different types of gates, and all these are different types of circuits. So here let us start with what is a logic gate. So a logic gate simply an electronic circuit. So it's an electronic circuit which operates on one or more signals and always produce only one output signal. So this is the definition of logic gate. Generally, a gate or a logic gate is nothing but a circuit which works on or operates on 2 or more inputs, or we can say 1 or more inputs, and always produce only one output signal. So that is a definition of gate, and it is used by the processor of computer system. That's what I have told you just now. So these type of circuits are present inside a microprocessor. So there we are using this type of system. And here gates are classified into 2 types. One is basic gates, second one is derived gates. Here there are 2 types of logic gates. One is basic gates, second one is derived gates. Basic gates are NOT gate. It is another name is called as inverter gate, OR gate, and AND gate. And derived gates means these are the gates derived from these basic gates. They are NOR gate, NAND gate, XOR gate. XO here X stands for exclusive OR gate and exclusive NOR gate. See, these are all different types of gates. In the next slide, let us see what is an inverter gate or what is a NOT gate. So the definition is a inverter is a gate which with only one input and always only one output signal. So this inverter gate which takes only one input signal and always gives only one output signal. So here the output state is always the opposite of the input state. So that is the definition of NOT gate. So here whatever the output is, what would be the output of this gate? So the output would be always the opposite or inverse of the input signal. So for example, now this is the logic symbol. This is how we represent the NOT gate or inverter gate. And here this is X and this is X naught. This is one output. So it takes only one input and it is one output. Here X is the input and output is inverse of X or opposite of X, that is X naught. And here now let us see what is a truth table now. Now the possible combination of these input variables are we are predicting inside table. It is called a truth table along with its output. So in this example, this logic gate takes only one input, and here if there is only one input and it takes, there are 2 possible states, that is either 0 or 1. So in this case, at a time it takes only one input, so the state may be 0 or maybe 1. So These values we are writing inside table, so this is called truth table. So in the truth table, we are writing the possible input combination of a variable along with its result or output. So in this example, as it's only one variable, so there are two possible states or two possible values, that is 0 and 1. Suppose if x equal to 0, the inverse of x is 1, so output is 1. We represent with x naught or x bar. And similarly, if the input is 1, output is 0. So this is an inverter gate or NOT gate. In the next slide, next one is OR gate. So what is OR gate? So here, the OR gate has two or more input signal, but only one output signal. So the definition of OR gate is it takes more than two inputs and always one output. And what is the definition? If any of the input signal is 1 represents high, the output is high. There are two or more input here. So if in the combination, if there are two ones, or we can say 2 1, here 1 stands for high and 0 stands for low, then output signal is high. That's the definition. Now let us see the logic symbol of this. See, if you look at this, this is two input OR gate. Here A and B are two inputs and F is the output. So this is two input OR gate and this is three input OR gate, because this gate takes two or more inputs, and this is four input OR gate. And all logic gates always produce only one output. That is, in this example, F is the output of these gates. Now let us see the truth table of this. And here there are two input combination. So normally we represent with the formula 2 to the power of n. That is, here n is number of input or number of input combinations. In this example, there are two combinations. There are two variables x and y or two input. So that is 2 to the power of n. That is 2 to the power of 2, that is equals to 4. So it is possible to have 4 different combinations for this OR gate. Accordingly, this is one variable x, y, and this is x plus y. Here the plus represents the OR operation. It is OR operation. So x plus y. And here there are 4 different combinations. This is 0, 0. If x value is 0, y value is 0, this is one status, or it is one state. And this is another combination, 0 or 1 or 0. And next one is 1 and 1. These are the different possible combinations. So in this example, if there are two input variables, it is possible to have 4 different combinations. So accordingly, so what is the output of this? As per the definition, if you look at the definition of this here, if the input signal is high, the output signal is high. If any of the input signal in a combination, so the meaning is it is a combination. In this 0, 0, it is 0. In this example, second combination, there is one input, one is there, and here is 1, and here is both of them are 1. In that case, the output is always 1. That is the definition of OR gate. So this is a truth table for two input OR gate, and this is similarly this is a truth table for 3 input combination. So here 3 input. Accordingly, if we have n equal to 3, here number of variables are 3, then 2 to the power of 3, that is equal to 8. So if there are 3 variables, we can have 8 different combinations. So accordingly, in this there are 8 different combinations for this, and this is the result, x plus y plus z, that is the output. Here this plus stands for OR operation. So this is OR gate. In the next slide, now let us see what is AND gate. The AND gate, it can have 2 or more input signals and always produce one output signal. And what is the definition of AND gate here? When all the inputs are high, output is high, otherwise output is low. The definition is when all the inputs are high, high represents 1. High represent 1. When all the inputs are high means 1, output is 1, that is output is 1. Otherwise output is low. Low in the sense it stands for 0. So accordingly, now this is the logic symbol of AND gate. This is 2 input AND gate, 2 input and 1 output. This is 3 input and this is 4 input logic gates. Now let us see the truth table of this. As what you have seen in the previous slide, there are 2 variables, 4 different combinations, and this is the output of this OR gate. And here the dot represent the AND operation, x dot y. Here that we have to read it as x and y. It is not dot. Dot represent AND gate. We have to read it as x and y operation. Now as per the definition, when all the input combinations are high, output is high. This is, you can see here in the last combination. Otherwise 0. So this is the definition. Accordingly, in this combination there are two combinations, 2 variables, both of them are high, result is high. And if you look at other combinations, here only one input is high and here no output is 1. So no input is 1. Accordingly, the result output would be 0. So this is the truth table for AND gate. And this is truth table for AND gate with 3 variables. As we have seen in the previous slide, if there are 3 variables, 2 to the power of 3, that is equal to 8 combinations, and this is the result of this. Even if you look at the result here, x and y and z, this is the output for 3 input variables. And here when all the inputs are high, only in the last combination all the inputs are high, the result is high, means 1. In otherwise 0. In all other combination, in this combination result would be 0. So this is AND gate. In the next slide we see what is NOR gate. So this is nothing but derived gates. See, what are derived gates? See, these are the derived gates which are derived from the basic gates. Any of the basic gate, that is a definition of derived gates. And one of them is NOR gate. What is NOR gate? And here the NOR gate has 2 or more input signal and always 1 output signal. And the definition, what is the definition of this? If all the inputs are 0, then output is high. That's the definition of NOR gate. And if you observe this, here derived gates, NOR gate. If you look at the NOR gate, NOR gate, and here we represent it as this is OR gate followed by NOT gate. That is how we represent the symbols. So if you look at a symbol here, this is the OR gate and this is NOT gate. So here NOT gate followed by OR gate, it is called NOR gate. And as per it, then this is the symbol, and we represent a single symbol with OR gate with a bubble. This is called a bubble. So this bubble represents, this is a NOR gate. So this is a NOR gate. This is 2 input, 3 input and 4 input NOR gates. This is a derived gates. Now let us see the truth table of this. 2 variables, 4 combinations, and here these are things here. Now as per the definition, if all the inputs are 0, output is high. Accordingly, in the truth table, this is a combination where all the inputs are low. Low in the sense it is 0. So 0 output is high. Otherwise 0. So this is a definition of NOR gate, and this is a truth table of NOR gate. And this is a truth table for 3 input NOR gate, and this is the output of this. So this is NOR gate, one derived gate. Next one is again NAND gate. This is another type of derived gate. And here NAND gate is nothing but this is AND gate. So this is AND gate followed by NOT gate. So this is a NOT gate, AND gate, and we represent AND gate with bubble here. So this represents your NAND gate. And definition is the NAND gate has two or more inputs and always produce one output signal. And definition is if all the inputs are 1, then or high, the output is 0. The definition is if all the inputs are 1, output is 0. Now look at the truth table of this. This is 2 input NAND gate and here 4 combination. Now accordingly, when all the inputs are high, result is 0. Accordingly, this is a truth table of this. So here, when in this example, all the inputs are high, result is 0. And similarly, this is a 3 input NAND gate. In this example, when all the inputs are high, result is low. This is, otherwise it is 1. So this is the truth table for NAND gate. Now let us see some other gates. Here, next one is XOR gate or exclusive OR gate. And that is, this is OR gate, exclusive OR gate. Now, it accepts 2 or more inputs and produce single output. This is the common definition for all logic gates. And the output is 0. Output is 0 if there are even number of ones in the input signal. So this is a definition of this. And output is 1 if there are odd number of ones in the input combination. So this is the definition of XOR gate, and this is the logic. This is the logical symbol or the symbol of XOR gate. Here this is OR gate, and here this is small r. It indicates exclusive OR gate. Here this is 2 input, 3 input, and this is 4 input logic gate. So this is the definition of XOR gate, and accordingly the number of E1s and number of ones are even or odd. So in this example, 0 is 0. 0 is 0 always. And here in this combination, if number of odd number of ones, here we have 1 is the output, and if even number of 1, it is here, and if there is odd number of 1, output is 1. Even number of 1, output is 0. So this is the input. This is the truth table for your exclusive OR gate. And again, this is a result of 3 input variables. And here the definition is when if the even number of ones, then output is 0, and odd number of ones, the output is 1. That is the definition. This is exclusive OR gate. Next one is XNOR gate. It is nothing but exclusive NOR gate. So accordingly, it is a gate followed, this is XOR gate followed by NOT gate or inverted gate. So it becomes XNOR gate. So the XNOR gate is logically equivalent to an inverted XOR gate. See, as per the definition, we can identify this as it is inverted XOR gate. So it produces high as input, as 1 as the output when there is input combination has even number of ones, or when all the inputs are 0. When all the inputs are 0 and an even number of ones and all the result is high. That is a definition of exclusive NOR gate. And this is the symbol here. This is OR gate, and this is OR stands for exclusive OR gate, and this is bubble stands for negation or NOT gate. So together this is the symbol for exclusive NOR gate. And in XOR gate we have no bubbles, but here we have a bubble. It stands for exclusive NOR gate. This is 2 input and this is 3 input exclusive NOR gate. And this is the truth table as per the definition This is the output of this, and we represent exclusive NOR gate with plus with a circle. This is exclusive NOR gate, and this is the truth table for 3 input exclusive NOR gate. In the next slide, now let us see. So far we have seen the definition of basic gates and derived gates, and we have seen the logical symbol and truth table for different gates. Now next concept is to design a circuit to realize the following equation. So this is the equation, this is called Boolean equation, is given to you, and for this we have to design a circuit. And here students, this is A B plus A C naught plus B naught A naught C. It means that this means that it is A dot B. Dot B stands for AND gate. And again this plus, this is plus, it stands for OR gate. So this is the combination, so it forms a one logic circuit. So here, again this is dot is in between. A dot stands for AND gate. A and C naught. This is OR gate. B naught, A naught, C. So this together it forms one circuit of the given equation. So accordingly, let us try to design the circuit for the given equation. So first one is A and B, as I told you. This is AND gate. This is AND gate, and AND gate has A and B. There are two input variables. So there are two variables here. So and output is always one. It is A, B, means that A and B, as we have seen in the previous slide. So this is the output of this. Next one is A, C naught. Here A and C naught, this AND gate, and here A, and this C naught is nothing but C bar or C naught, that is NOT gate. So this is how we represent C naught. C naught, and output is A, C naught. And again B naught, A naught, C, means that B naught dot A naught dot C. So dot stands for AND gate. So in between we have AND gate. So this is a 3 input AND gate. Accordingly, B, this stands for B naught, A naught, and C. And this would be the output of this. And all together, so it's a combination of plus is there. Plus stands for OR gate. So output will, all the output of these gates will be the input of this OR gate. So this is OR gate. All this are input, and it produces one output. That would be the same equation what we have given here. So this is how to design a electronic circuit or digital circuit for the given equation. So this is the circuit has been built or written by using basic gates. So this is how to write how to design a circuit for the given equation. Students, next concept is universal gate. So what is universal gate? A universal gate is a gate using which all the basic gates can be designed. And here NAND and NOR gate are called as universal gate. Now students, we have seen the definition of derived gates. So what are derived gates? Derived gates are derived from basic gates. I mean basic gates are NOT gate, AND gate, and OR gate. But what are universal gate? Here there are two gates, NAND gate and NOR gate, are called universal gates because by using these two gates we can derive basic gates, that is AND, OR, and NOT gate. That is the definition of universal gate. Here NAND and NOR called universal gates, and here these are the more popular as these are less expensive and easier to design. And the basic gates AND or NOT can easily be implemented using these gates. And that is the reason we say NAND and NOR gate are called universal gates. Now let us see how do we derive the NOT of, now let us see the operation, how can we derive basic gates with the help of NAND gate. So this NAND to NOT logic means how do we design, how do we conclude, how do we write a circuit for the NOT gate by using NAND gate. So here look at, this is the equation, we can write algebraically, and here look at the diagram here. So the result is, if you look at the NOT gate, it takes only one input and always it gives one output. So output will be the inverse of input or opposite of input. Accordingly, suppose AND gate, it takes two input. So we have to join this to form one output here. So this is one output and result is X0. So this input is X, output is X0. So this is the same result as we have gotten for NOT gate. NOT gate, it takes only one input and always one output. So this is, so with the help of NAND gate, we have derived the result of NOT gate. So that is the meaning of NAND to NOT logic. Next one is here OR operation. So how do we design a circuit or operation of OR gate by using NAND gate? Here this is a NAND gate, and again this input is X and input is Y, and finally we have to get the answer as X plus Y, because in OR gate there are two inputs. Here X plus Y would be the result of the OR gate. Similarly, but here we are using NAND gate here, and here is only one output X. So normally NAND gate would be having two inputs, so we have to short this or we have to combine this to form one single input. So this is one single input. Output would be X into X0, and this is Y here, Y into Y0, and finally this is X plus Y. This is the result of OR operation. So this is a circuit for NAND to OR logic. Similarly, this is AND operation. In AND operation, again the NAND gate, it is X. There are two inputs, and this is another. Again, the output of this will be the input of second NAND gate. It produces the result as X and Y. So if you observe the result of AND gate, it takes two input X and Y. Output would be X and Y. So this, the result we got it through the NAND gate. That is why it is called as a universal gate. So in this example, we have seen how do we convert the NAND gate into basic gates, NOT, OR, and AND gate. In the next slide, we will see NOR to NOR logic, or we can say with the help of NOR gate, how do we derive basic gates and OR and NOT gate. So accordingly, say as we know, the result of operation, suppose in result is input is X, output is X0. So this is, we have got it, we can prove this algebraically, but how do we design a circuit for this? So this is NOT logic. NOT gate, it takes only one input, but here this NOR gate, it takes two input, and we have to join these or we have to short these two inputs to form one single input. So single input, output is X0. This is the output of NOT gate. And similarly, this is OR operation. How do we derive at the OR gate or OR operation? By using NAND gate. So this is the circuit here. This first NOR gate, it takes two input, and because of this, output would be A plus B NOT. And again, the output of this would be the input of one more NAND NOR gate here. So this is a two gate here, but output is one. We have to short this or we have to join this to form a single input to this gate, and result is A plus B. So AB is the input, output is A plus B. This is the result of OR operation, and that is we have got it through NOR gate. So this is NOR to OR circuit. Next one is NOR to AND circuit. Next one is how do we design AND circuit by using NOR circuit or NOR gate. So here this is the equation, and here observe this, there are two input here A, B, and output is A and B. See, this is the result of AND gate, This is the circuit for this. This is NOR gate. It takes 2 input, and to get separate input, one single input, we have to short this. So this is one gate, input is A here, and this another NOR gate, input as 1, B is another input. And after this, the result of this, always this is one output. The result of these 2 gate, it goes to another NOR gate, and the output would be A and B, or A dot B. So this is how do we convert or how to design AND gate through NOR gate. Students, so far in the chapter logic gates, we have learned the definition of logic gates and basic logic gates, derived logic gates with the logic symbol and truth table. And also we have seen, other than basic gates, we have seen universal gates. They are NAND and NOR gates, and those 2 are called universal gate. And also we have seen the circuits for how do we convert or how do we derive basic gates from NAND gate and as well as NOR gate. Now let us continue our discussion in my next session. Thank you so much.